Good, thanks. Yes. So I do understand, even if we're a small, it's quite diverse audience from different fields. So I'd like to make it at least the first half of it. Hey, Frank. Hey. So to make it as pedagogic as possible. And also, as I'm leaving later on today, I'm happy to answer any questions you might have during the talk. So do feel free to ask anything. So the first, I mean, most of it, it's simple. Let me give you a bit of a background about the picture. This is the Colossus of Rhodes, one of the 7 ancient wonders of the world. I come from Rhodes. I'm not one of the wonders, but Colossus is. It was a huge statue that made out of bronze that used to stand in front of the harbor. Actually, this harbor or a similar one exists now in Rhodes. Very beautiful with castles all around. And it served as a symbol of power and prosperity, but also as a lighthouse. It had a fire there, and the ships could guide and navigate around these quite treacherous waters, actually. The area is seismogenic. There are many earthquakes. Come in, please. It is a thing. This is an artistic impression. It might be like the Statue of Liberty. There is a staircase inside. So the thing is that we have no physical evidence of it. Yes, no physical evidence whatsoever. But there are 3 independent historical evidences. I mean, whatever. This is Rhodes the Colossus, right? Yes, I grew up there. Yes, I beat you. Yes. So the historical evidence. So the historians of the time, they wrote about it. And apparently, there were 3 independent ones, and we compare what they wrote, and it seems to agree actually to that it should exist, so that they are in agreement. You know that they didn't copy each other. It might have been, but like scientists, I don't know. Yes. Now the area is seismogenic. There are earthquakes, so probably a big earthquake happened. You fall down. Copper it was like gold back then. It was very valuable, so you wouldn't just let it lie down there. You melt it, make tools, weapons, or whatsoever you needed. So that's why there's no physical evidence of it. So I like this story very much because it reminds me a little bit of non-abelian anions. It's something that we talk about. We want it to exist, or in a hard to exist, but in reality we haven't found yet conclusive evidence, or the community is very, we can vote if Colossus exists. I do that quite often in my talks, my popular talks, and half of the people believe it exists, half they don't. So here, yeah, the same thing with anions. What my efforts are, I decided to work on bridging some of the mathematics and the models that give rise to non-abelian anions, these exotic quasi-particles, to physical realizations, talking to the experimentalists, convincing them to do certain experiments and why they're important and why they help. Now, the experiments, they are quite advanced, but still we need a lot of work to realize non-abelian anions. Why we're interested in them? Well, it's a new particle, quasi-particle. Is exciting to realize something that is not boson or fermion. And second, very, very mathematical. So having these very weird properties emerge in a physical setting is quite exciting, quite interesting. It will give us yet another toy to play and study. And third, there are promises that it can help on quantum computation. So the idea is that we encode information in these quasi-particles, and as long as these quasi-particles are not destroyed by the environment, their nature is preserved, the information is preserved. Also, the gates, the quantum gates, are done by braiding these quasi-particles. So the statistics of these quasi-particles is complex, is the quantum gate. So you use fundamental properties of particles to encode and manipulate information. So as long as the quasi-particles, their nature is intact, the information is intact. So that's the promise, the idea. Reality is much harsher, of course. The information is not that robust. Anyways, what I want to do today is to give you a brief overview of topological quantum computation or quantum computation with anions. Then I'll pick up one rather simple but also very powerful model, the Majorana fermions as non-abelian anions, and explain to you, and hopefully by the end of the talk you'll say, yes, I know why they're non-abelian anions and how they behave and so on, from just fermionic operators. So I want to do that really in detail and slowly. Then I'll explain how we took this idea to the lab, and we performed certain manipulations, and we demonstrated certain properties of non-abelian anions, of Majorana fermions. So I'll show you slides with data and so on. So, and also, I would like to tell you a little bit about DS3 anions, some quantum double anions that we became interested recently. We did some experiments with them and some surprising resilience. So, some of the results I want to tell you is not only that they're experiments, but by doing the experiments or by studying the physical setting, we discovered some new type of robustness that emerges that is not related to topological properties, it's related to actually encoding information into larger Hilbert space. So,
experiments you mentioned, they are simulations, or they are experiments in the lab with low temperature and so on?
There are simulations with photons or with superconducting qubits. But there are simulations. We do the quantum gates, the quantum states, rather than realizing Hamiltonians. That's right. Yes, yes. They're not. We don't realize Hamiltonians. But still, very good question. Some of the protection comes because you encode things in the ground state, and you expect the Hamiltonian with the energy gap to keep it protected. This type of protection is against perturbations. So if the energy gap is not bridged by external coherent perturbations, then the information is robust. Nevertheless, this doesn't protect you against thermal errors, probabilistic errors. This happens if you have energy gap or not. I mean, it might reduce the probability, but it will happen. So really, topological systems do not, strictly speaking, protect you against thermal error. It's possible to consider fractons, which actually, there are some special case of topological particles that protect you against thermal errors, either in 2 or 3 dimensions. So some generalizations. The type of protection I'm going to present at the end is against probabilistic errors, actually, and this is something rather surprising. Doesn't have to do with topology or energy gap. Yeah, what do we see here? My colleagues in Hefei that I visited once do the experiments. Also, experiments are done in UK group with Mehul Malik's group, photonic system. And most recently, we are carrying experiments with IBM superconducting quantum computers. And there is awfully many people actually in that. You might have heard recently some experiments in the past couple of years. Google and Quantinuum, they perform non-abelian simulations of quantum compute of anions, simulations of non-abelian anions. And there was a lot of talking about it in the media, and I was conducted by reporters, journalists to say something so they can write popular articles about them. And of course, the journalists wrote the things I didn't want them to write. They picked up on the words or on the phrases I was actually correcting. But that's what they want, controversial things, as typically want. They are simulations. They're not the actual thing. But of course, the boundaries between the actual thing and the simulation are not very clear. Okay. Pardon?
What do you mean by that?
Yes, very good question. The thing is that, do you need a Hamiltonian when you're doing anionic systems? I do not know, because a topological system shouldn't have a Hamiltonian. Hamiltonian is equal to 0. So it's the states really the important thing. Do you need to have a two-dimensional configuration of qubits or qubits in order to braid anions and so on? Well, I mean, some of the experiments are done in one-dimensional chains. So how could you braid in one dimension when? So basically what they do, they encode the 2 dimensions to 1 dimension, and they manipulate things in a certain way. Well, if a system is topological, it means there is not a metric. So it means it's not geometry. You can arrange your things as you like. As long as you know who is what and where they are, and you have a certain order, then things will be all right. So you see, the boundaries of what should be topological system are really not, are very flexible, let's say, not well defined, at least. So let's say that we care that 2 things. We would like to discover the fundamental properties of non-abelian anions. That's one thing. Another thing, we would like to construct a device which is robust against errors based on non-abelian anions. That's a different question. Okay, so we shouldn't mix the 2 when we're looking at simulations or experiments. So for me, these experiments are fantastic, and they do achieve their goal. Are they robust against quantum computation? Not really, or at least not as they are. Let me tell you a little bit about topology. Yes, simple. Here's a cup. There's a cup. You can fill it up with water or coffee. But as you hold it, if you change the geometry of your fingers, this cup might just fall down. Okay, so it's not protected. Now, if you have a handle, you can put your finger around the handle. All right, and as soon as you linked with the handle, change the geometry of your fingers without actually breaking the connectivity with the handle of the cap, will not make the cap fall down and break. So it's protected. You must spill the water, but you're not going to break the cap. And here is another cap I like very much. It has 2 handles. So if you pass a cup of tea to somebody, they don't have to burn their hands when you're holding on the other side. They grab the other handle, very civilized. Or you go to your office and you have to, the keys are on the opposite pocket, you change. Very helpful to have 2 handles in a cap. This thing is just a show off, right? There's no reason to have 3 handles. I don't know why people made this. It's just embarrassing. Yes. So topology. So in quantum information, we use it in very, very similar way to what I described here. Being able to have a linkness actually creates the protection to the quantum information very much as with the gap. So we would like to take advantage of that, and also topological effects are lots of fun. I hope I'll convince you about that. What's the difference between geometry and topology? Well, let me use strands and links. These 2 strands that create this link. It's geometrically is not equivalent to this one. these two geometrically are different. You see the local curvature is different, but topologically they are the same. If you go around this strand, you see you have 6 different, the same orientation kind of exchanges similar to that one. So topology tells you that these are equivalent. You could define the Gauss curvature on the link, on the 1D, embedded into the 3D space. Yeah. You put a frame on it, and then the derivatives of the vectors on the frame. So you have a tangential and a vertical. That's right, the Gauss, that's right, yes, the linkedness is the same. That's right, yes. The Gauss number of these two is the same. Okay, the integrated, so the Gauss is the integrated geometry is the same. The local geometry is not the same. Yeah, but the integrated, and indeed topology is the integrated geometry. Some information, so that's the interesting thing really. There's lots of information here and lots of information here. Topology, that is described by geometry. Topology doesn't care about this local information. It cares about some global ones, some integrated properties. It's very similar to, language recognition methods where you can say yes or no, and you can Fourier decompose it to different frequencies and so on, but actually what you care about is only a 2-bit of information, a yes and a no. So the same thing with topology. Extracting the topology is a hard, complex thing. But let me proceed. Typical topological effect is the Haranoff bomb. You have a solenoid of a magnetic field, and then you have a charged particle that moves around. The particle is trapped, and you move it around. The wave function acquires a phase factor, and importantly, it has an integer and which cannot be deformed continuously. It's a number of windings, and the integer tells you that you have a topological effect. For 2 identical particles, the statistics tells you if you exchange, so you describe them, the system of 2 particles with a wave function. If you exchange them, and you close your eyes, somebody exchanges them, you open your eyes, it looks exactly the same. So while they look the same during the exchange, it means that locally you go and measure one, and you'll measure the other, and you find exactly the same answer if they've been exchanged or not. But the wave function that describes them might actually change in a way that if you measure this wave function locally here or locally here, you won't see this difference. But it might be an overall change. For example, you could have an overall phase factor in front of the wave function. And of course, that's not measurable locally. And that's what statistics is. That's how it emerges, this symmetry. We will be interested in 2 exchanges. And if you do 2 exchanges, that's equivalent to, if I exchange something twice, it's similar to moving one around the other. And that's easier for me to play with this setting of moving one particle around the other. I'll be focusing on that. And in 2 dimensions, the moving one particle around the other cannot be continuously deformed to moving a particle, just a smaller circle there. So if it moves around the other, and I'm assuming that the particles are hardcore, they can't penetrate, they can't go through each other. It means then this path cannot continuously be deformed to the other path. Also, I don't care about interactions between them. So I can change the shape of the path without actually changing the physical consequences of this evolution. So while the small path I can deform to the trivial one, like doing nothing, the larger path I cannot. So actually I can assign a phase factor or a whole unitary in the evolution of the bigger path compared to the smaller one. And that's what anions are. And that you can do only in 2 dimensions. In 3 dimensions, you cannot always lift up on the 3rd dimension and then deform it. which means that you can have only bosons of fermions. But in 2 dimensions, you could have bosons of fermions, or you could have more things. And the thing is that, of course, we don't live in 2 dimensions, we live in 3, but quantum physics has this nice property of separation of variables method, which tells you that you could have, if the system is translationally invariant, or you can squeeze it really much, there is a wave function that lives exclusively in 2 dimensions. It's a 2-dimensional wave function. And if you manage your interactions in these 2 dimensions in a particular way, then you can make this function believe that it's anionic, yes, a wave function of anions. And that's really the ingenious thing. If you want a mechanical analog of what anions are, you can think of them as being punctures that have some magnetic flux that goes through them. And then there is a ring of charge around them. So when you move this one around the other, the charge of this goes around the flux of the other. Hence, you'll get a phase factor by this exchange. And it doesn't care about the shape of the path. It cares that you went around. Now, this might look a bit mechanical, like how is it possible to have these things? But that's exactly what happens with the fractional quantum Hall effect. There, you have a 2D system. You have vortices. The vortices are punctures that allow magnetic flux, integer fluxes of 2 pi going through them. Actually, the fractional quantum Hall effect traps charge around the vortices. And this charge needs to be fractionalized in order to see a non-trivial phase factor. If it's not fractionalized, then it gives you just a 2 pi phase factor, which is trivial. But if it's fractionalized charge, then it goes through the integer multiples of 2 pi flux, and you get some non-trivial phases. That's why we cared about the fractional quantum Hall effect. And another way how so this will be actual realization of the Harrow-Bohm effect. Another way to see it is as a geometric phases. So you can think that the parametric space is the position of these particles. You change your Hamiltonian in a particular way, you can get abelian or non-abelian phases out of it. And most of the cases, for most models which are non-stabilizer, that's how you calculate the statistics of anions. What's that? An overview. Wow, look at that. I will talk about topological phases of matter, Majorana fermions of the DS3 model a bit, and in particular, I will show you how we simulate them by using spin systems, or that can be easily encoded in simulators like photonic systems and so on, or superconducting system. Typically, what you have is a 2-dimensional system with many particles that they interact in a certain way. And then you create some quasi-particles. These are like collective effects of the particles of your system, like vortices, for example. And if you have vortex in the water, you stop caring about the position of the water molecules, and you say, oh, my vortex is here. And then you can forget the background, and then we'll be interested about the behavior of these vortices and their properties. Okay? But it's really a wave function of the many particles that gives rise to the properties of the vortices. And that will be the anions. Yeah, spin half particles, you're good with that. So let's move to a fermion now, all right? So start with fermions. I'll take you to Majorana fermions. I'll take you to Hamiltonians of Majorana fermions. And then we'll see how the anions as Majorana fermions emerge, okay? And their statistical properties and their fusion properties. Just simple calculation you can carry out in 10 minutes or hours, doesn't matter. Yeah. If we have a fermionic mode, it can be either populated or empty. And you have the creation and annihilation operators that move you between them. There's 2 states of 0 and 1. Okay. Now, and we have this commutation relations of fermions. Okay. So what I want, what am I doing here? Why am I moving like that? Okay. 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 Now we'll consider a special Hamiltonian between two fermionic modes. I have fermionic mode 1 and 2. And I have a Hamiltonian like that. It has these tunneling terms that take one fermion from one side and move it to the other, and the other way around. And this superconducting or pairing term that tells you that if I have two fermions on each, one on each mode, this can combine together and go to the vacuum. Okay, or from the vacuum you can have a creation of two fermions actually. So what I'll do is from this Hamiltonian that describes fermions, I'll rewrite it in two different ways. I'll write it as a spin Hamiltonian using a Jordan-Wigner transformation, and I'll write it as Majorana fermions just by decomposing normal fermions into Majorana ones, into its real and complex parts. This one, I like it because, this description, I like it because quantum simulators or quantum computers can encode spins. These are your qubits. This I like because these are Majorana fermions. That's the holy grail. That's what you want to achieve. So writing this in two different ways, it means that you can connect properties of a spin system to properties of Majorana fermions. And that's what we'll do. We'll manipulate things on this side and interpret to manipulations of Majorana fermions. Yeah.
You should equally be excited then if you can do this on a classical computer.
You can do it on a classical computer.
Because it's also.
That's right. We did it.
It's not a real Majorana.
Too many questions. First of all, we did it with classical light and was published in PRL because we could do it classically. So the referees were excited about that. First, okay. So now you learned something about the fundamental properties of Majorana fermions. So I am excited because it became a paper. So second, what was the second part of your question?
You can do it just over a computer.
Yes, that's right. You can do it with pen and paper. That's right. You can do it with pen and paper. So what's the value of actually doing it in an experiment? The idea is that, first of all, the classical can become quantum, and that's what you want to do because you actually encode information. Second, if you do it with two or a few fermions, it means that you can, in your quantum simulator, the method then to extend to larger systems is straightforward. Just scale it up. As the hardware improves, you can add more of them. And then you have an actual anionic quantum computer. So it's not, having the prototype is not a trivial thing. Yes, that's right. I will describe that. Yes, exactly. Yes. Yeah. I mean, first of all, you could restrict. So this one indeed has a projection there to parity. This does not, but you can apply a parity projection to this one. Now, what you want to do is, I'm not saying that this is protected with parity. So a lot of the protection of Majorana fermions is because of the parity projection that keeps things in one state and doesn't allow it. Here you don't have this, okay? But again, I'm not interested about the protection for quantum computation per se. I'm interested to realize some of the physics, like the statistics, the non-abelian properties. If you like, I will imitate this system with this, and if this gives me non-abelian Berry phases, this will give me non-abelian Berry phases. That's for sure. Yes. So I'm doing holonomies, non-abelian holonomies, actually. It's a unitary transformation that maps. It's a unitary transformation that maps something which is protected against local errors in space. Local errors in space here become non-local errors here, okay? But it protects against these non-local errors. So deformations in the paths of this one corresponds to deformations in the paths of this one. And so it's topological. If this is topological, this is topological. In terms of errors in space, this protects against them, this does not. Okay? I'll show you a picture of that, actually. So the topological properties of the evolutions here are exactly the same here. But these are evolutions in space. These are evolutions in some abstract Hilbert space, parametric space of the experimentalist.
When you say geometric phases, because this is what you call Berry phases, right?
That's right, yeah. Or holonomies, yeah.
It's not the same, because
Potatoes,
well,
tomatoes.
when you talk about geometric phases, it has to do with the changing parameters adiabatically.
That's right. Yes.
This is I'm familiar with. But then I think when you were talking about the Aronoff bomb effect, when you use the word topological.
Yes. So Berry phase is a topological phase.
The Berry connection does not have to be flat.
Yeah, it is what I want it to be. Yes. Yeah, nice. To be like Trump. Nice. So I explain. Very good. Yes. Good question. So imagine that I have a magnetic flat everywhere. So if you make a path, then the phase you obtain out, the phase you get depends on the size of the path. So this is equivalent to a Berry phase, that indeed it depends on the size of the path and the position and so on. So it's the geometrical characteristics of the path. But imagine that for the Aronoff bomb effect, you have to confine the flux in a certain region, and then you make the path around it. Now, it doesn't matter the shape of the path.
It actually is flat outside.
It's flat in this. Now, imagine that I can construct a quantum system that has a Berry connection that is confined in a certain region or some parametric space, lambda 1, lambda 2. It's possible. Nobody says it's not possible. You could do it. And that's what anionic systems are. They confine the flux of the Berry connection in a certain region. And actually, these are x and y position. For example, the abelian anionic properties of the fractional quantum Hall effect are calculated as Berry phases in the seminal papers by some smart people. Yeah, it's cool.
So yeah, so Berry. So the point is that we're looking at holonomies of flat connection.
Yes, yes. Holonomic flat connection, which is non-flat in certain region.
It's not just Berry phase, it's just a particular type of Berry phase.
Yes, yes, yes.
Yeah, have not told us about.
Yes, 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 exactly. That's why I'm here. Yes. I have something to contribute. Frank is skeptical. Where are we? Where are we? Where are we? We are. What am I doing? Yeah, I'm here. Yes, all right. Let me take this part. You guys don't mind about time? I don't know what time it is. Yeah, you're good. Yes, you're having fun. All right. Open your laptops. Yes. I want to keep you a bit more here. So first of all, let's take the Jordan-Wigner transformation and transform the superconducting Hamiltonian into spin Hamiltonian. And for two spins, the Jordan-Wigner transformation is rather simple. A1 becomes sigma 1 plus, and A2 becomes sigma z, sigma plus. Okay, it has this string sigma z in order to encode. You see, spins are commute with each other, but if you add a string, they don't commute anymore. These operators, they're fermionic. And if you substitute this in the superconducting Hamiltonian, very nice cancellations happen, and it can be written as sigma x, sigma x. And this is a rather simple Hamiltonian to realize in the laboratory. If you ask an experimentalist to realize this Hamiltonian, they will freak out because pairing terms are really hard to do in the lab. But you can make this transformation, and this, they tell you, yeah, I can do that. I can do the ground states of that. Now, you can this Hamiltonian has the plus plus and the minus minus as the general ground states, and the others are the excited. And the logical information is encoding it in these two ground states. Okay. Now let me take the other path. Let me move to the Majorana fermions. And if you have a mode A, Majorana fermions are like the real and imaginary decompositions of the fermionic modes, A plus A dagger and A minus A dagger divided by I. And these are called, so one fermionic mode has two Majoranas describing it, gamma 1 and gamma 2. And they are Hermitian operators. Gamma dagger is equal to gamma. Okay, so its annihilation operator is the same as its creation operator, and that's the yin and yang kind of equivalence. So nevertheless, this is just a mathematical construction. It doesn't have any physics here, right? I mean, it's not like I have Majoranas when I have a real fermion. But what I'll now do is make Majoranas physical. And indeed, I needed this Hamiltonian. If I decompose now, and I'll tell you what I mean physical, yeah? If I decompose both A1 into gamma 1, gamma 2, and A2 into gamma 3, gamma 4, then A1 is gamma 1 plus I gamma 2, A2 is gamma 3 plus I gamma 4. You substitute everything there. And
Gamma 1 plus I.
Yeah, it's gamma A dagger, yeah. The dagger. The dagger hits the plus and makes it minus. Yeah, it's all right? Yeah. No, it's correct.
Yeah, that's exactly what I said.
No, but it's both daggers there. It's dagger, yeah. Be sure it's surprising that I got it right, yeah? Be sure. And let's celebrate it. I'm prone to errors all the time, but I have my students like Frank correct them, yeah. Yeah. So now if you do this calculation, you see that actually the Hamiltonian becomes gamma 2, gamma 3. A very, very simple Hamiltonian again, like the spin Hamiltonian I had there. And let's look at it. So here is gamma 1, gamma 2 for this guy. Here is gamma 2, gamma 3, gamma 4 for this guy. The Hamiltonian is actually acting between these two. And these two Majoranas now are at the end of my system, okay? And actually, look at it. There's gamma 1 here, gamma 4 here. They are delocalized, okay? So if I write if I now define a new fermionic mode, B1, to be the superposition of gamma 2 and gamma 3, these two, then my Hamiltonian is only a function of this B1, B1 dagger plus B1, plus a B, or B2 if you like, that is a superposition of gamma 1 and gamma 4, but with zero energy, so it's not there anymore, okay? So this is, if you like, a geometric way how to diagonalize a Hamiltonian. You say, oh, all right, I had this one together here, but now if I combine these two, that's the only thing that interacts. So I have this one, so that's my Hamiltonian, and these are my degenerate states of my Hamiltonian, or a mode that, if it's occupied or empty, doesn't change the energy. And this actually picture that what we did here tells you two things. Majorana, first of all, I managed to delocalize the Majorana fermions. It's not anymore a mathematical object of decomposing fermions in two. Is physically, I have a mode, a fermionic mode, with one Majorana here and one there. I managed to move them away. So as if I can go and study each one now in position, yes? As an eigenstate of a Hamiltonian, actually. First. Second, they live at the ends of my chain. So these these Majoranas is at the end. If I had bigger chains, this would be farther apart. third, they're called zero modes because there are zero energy associated to these ones. So the energy you're, if they are populated or empty, they don't change the energy of your system. So they are called zero modes. So you get all these beautiful properties out of it. If you like, you're interested in trivial and non-trivial Hamiltonians. The trivial ones is when the interaction is between these two, like local chemical potentials. And when the interaction is between these two is non-trivial, and the Chern number changes when you move from one to the other. And that's why you get these zero modes. What are Majorana fermions? Well, these are very cute things we like very much, but they're very, very fragile. So people discovered them in this one-dimensional superconducting materials, but as zero modes, as you see here, with these populations firing up. But people were very skeptical. So we decided, so these are physical Hamiltonian kind of simulation or realizations in the lab, but people are very skeptical about this because they say, oh, there are so many different effects. You haven't seen the braiding, which is the important characteristic. You've seen the states, and they shouldn't be there for the temperatures we have. So people really fall on the experiments and they kill them. The same fight. Yes, in the community, very strong. So we decided to, yeah, and all following experiments. People, yeah. So the systems are too complex. There are many effects. So now people can explain them with alternative ways. That doesn't mean that what they measure is no Majorana, but they couldn't exclude the other effects. Okay. Also, they appear at temperatures we don't expect to see Majorana fermions. So these were like either super robust for reasons we do not know, or there are no Majorana fermions. So they observed zero modes. Okay. The conclusive thing is to do the braiding in order to observe it. So what we said is like, okay, let's forget these axial realizations. Let's do quantum simulations where we can actually do the braiding, and let's see these effects happen. And of course, we're going to use spin systems. And here is a slide for Frank. So indeed, axial fermions, axial Majorana fermions, you braid them, you create them in pairs. These are word lines. You braid them here, exchange them twice, and then you recombine them as time evolves. These are word lines of them. You start from the vacuum. You end up to the vacuum of some fermion. So that's what Majorana fermions would do. By doing a Jordan-Wigner transformation, you unitarily change this evolution to some other evolution with some parameters lambda 1, lambda 2. Still, there are very well-defined paths. You do in the control parameters of those. You do the same experiment. If you make errors in the position of the paths, then the final answer doesn't matter. That you have exchanged them is important. You have exchanged this path. So the topological aspect is there. Now, people call topological protection also that if errors happen locally in space, in position, yeah, the environment just goes and acts locally in space. Local errors here, and this topological system protects you against local errors here. Yeah. Here, they don't protect you against local errors, because local errors in position space, they're transformed to non-local errors here. But we're not dealing with error protection. We're dealing about topological. So if that's topological in space, this is topological in some other parametric space, because the Berry phase is still confined in certain region. Let me now give you two slides which tell you why these are non-abeliananians. Okay? And the reason being that, let me use four such Majorana fermions. I have a chain here, another chain here, and I connect them with a material as well in the middle. Now I have four Majoranas. I compare them either horizontally and create these fermionic modes A1 and A2, or I compare them vertically with fermionic modes B1 and B2. Now, the A's and the B's are not independent, okay, because they're all described by the same four Majoranas. So basically, they have funny commutation relations. But you can show that populations of one populations in the B mode, okay, are actually superpositions of no populations and double populations in the A mode. Just do the calculation. You play with the operators and the states. You construct this basis in A modes, and you construct the base in the B modes. And if you transform the back and forth from the A's and the B's, you see that populations in the B mode is superposition of populations in the A mode. And the same thing for the, this is the 1, 1 in the B direction. This is the 0, 0 in the B, has a minus sign. And it's interesting, so changing from one to the other is a rotation. So you can go from 0, 0 and 1, 1 of the A modes to 0, 0 and 1, 1 of the B modes by this unitary transformation. And that's what we call the F matrix or F symbol, or the fusion symbol of this anion. So I can describe them as non-abelian anions, if you like. What it tells you is I can prepare the system in a certain state in this direction, and then if I measure in the other way, I can find them both empty or both filled up. Okay, so both empty means I don't have a fermion. If they're both filled up, it means I found a fermion. Even though if I prepared them in the vacuum state in the vertical direction. And this doesn't violate the parity because the parity is preserved. It's zero parity or even parity in both cases. And this is the fusion rule of, non-abelian fusion rule of Majorana fermions. You put two Majorana fermions and you find either the vacuum or a fermion, an actual fermion. And of course, this is doubled. I have this property on one side, and of course, I get exactly the same thing on the other side. So these are mirroring each other because the total parity being vacuum. Now, after verifying the braiding, the fusion property, let's see how the braiding, the non-abelian braiding, emerges. And what I want to do is to exchange the position of gamma 1 and gamma 3. So I have this anionic change. I can exchange them by moving gamma 1 back, moving gamma 3 across this line to the position of gamma 1, and then move the gamma 1 down and where the gamma 3 was. So I can exchange the endpoints by moving them in this tree diagram, if you like, this connected graph. Now, if I exchange gamma 1 and gamma 3, I can write the unitary that describes this exchange by an operator that depends on gamma 1 and gamma 3. Okay, if no other operator is involved, then I can write them in terms of gamma 1 and gamma 3. Now, another property we should bear in mind is that gamma 1 squared, it gives you 1, and gamma 3 squared is also giving you 1. So this unitary, you can expand it as a function, to be a polynomial of gamma 1 and gamma 3, but it's truncated to only bilinear terms. You can't have higher orders because this Majorana fermion is squared to 1. So it can have only 4 terms, and then put some complex phase factors, A, B, C, and D, some complex numbers. Should not be allowed. This is a unitary. So the unitary can be written as functions of this. That's right.
This would allow you to make selection.
That's right. So when I say unitary, I mean that let me.
Unity transformation you can actually implement should be quadratic.
The effect, no, the unitary could be a single gamma. The effect should be quadratic. So what the Hamiltonians you have.
Super selection rule and all your operating.
Yeah, it's super selection rule of the Hamiltonians or on the states, but the unitaries could be anything. But you want. That's right. Yes. Well, that's right. A super selection rule could have made B and C 0, but let me keep them there for completeness now, okay? Because I'm playing a mathematical tool. I could have simplified the calculation by removing them. Sure, fine, okay? But let me keep them there. First requirement is that this U is a unitary, so I need to fix what A, B, C, and D are. So I demand unitarity, and also I demand that when they act on gamma 1, it takes gamma 1 to gamma 3 or something proportional to it. When I act them on gamma 3, it gives me gamma 1. So basically tells you that you exchange them. Okay, that's what this unitary is there for. And there are two possibilities actually.
You are trying to describe the operator
That's right. I'm describing the operator, the unitary time evolution operator that describes that I had gamma 1 and gamma 3. Now I have gamma 3, gamma 1. Yeah? Exchange them. And this unitary actually, if you indeed, of course, it does satisfy the super selection, what you find at the end. I could have imposed it and made my life simpler from the beginning. You're right, Frank. Thank you. But what you find is indeed the square of it, because I'm interested of two exchanges, is either a phase factor or this manipulation, this pairing term, if you like. And what we have implemented the experiment, and this became a nature communication, this just a phase factor. Basically, this solution, you get two solutions here, this and that. This solution corresponds if you exchange two Majoranas at the ends of the same chain. And because of the parity, which is fixed in a single chain, you just get a phase factor. You can't change the number of fermions. But if you exchange two Majoranas on different chains, then you can get something that changes the state of your system. And this is your non-abelian evolution, yes? Just because they are Majorana fermions. It's, again, a very simple exercise. You can find it in my book. And this became Science Advances. This is a bit of the Hamiltonians that we simulate. Basically, we simulate the ground states of the Hamiltonians and we manipulate them. And it is really a Berry phase where we change things and we calculate that as a geometric phase, as you see there. So yeah, if you don't want to call them Majorana fermions, you can call them non-abelian phases. And we made these different evolutions. This is experiment. One had 3 spins, and then and this is the phase factors, and then we had 5 spins, and we made different evolutions. The system.
Okay, so what you did is by mapping it to.
That's right. Yes, that's right. Just doing John Wigner, but. That's right. Yes. So. Oh, that's right. Yeah, yeah. I mean, so this is Majorana. Let's say. You need to do, and then a fermion here. Then there becomes a spin chain with another spin here. So the mapping, the non-locality is between these guys that changes. So a state which is localized here becomes global state on the whole system here.
But you have to choose an ordering of your nodes. What is the ordering of your nodes?
Oh, that's right. Yes, yes. 1, 2, 3, 4, 5, 6, 7. That's right. Yes. Yeah, yeah, that's right. Yes, you need an ordering. But these 3 diagrams are easy to order, really. Yeah, that's the. Yeah, this is the experiment. I took a picture. I took it proudly. And we verified, for example, you can verify different properties. So for example, if you do local errors, so you encode information, these Majorana fermions, and then you do errors on this one, that you can Jordan-Wigner transform the error and become some correlated error on this side. But you can show that the information you encoded on the spin is protected against the correlated error that is mapped here, so, which means that this is protected against local errors. So we performed different errors on the different spins here, or even some correlated errors, and we demonstrated that it's resilient.
And the Microsoft people wanted to create this with actual Majorana.
That's right, yes.
And why would they use this and how would they use this?
That's right. So what the Majorana, the Google people did, the Microsoft people did, is in the lab. So they did it with superconducting Hamiltonians. This is the photons. Yes, that's all experiments are done with photons. That's right. I did, yes. No, my friends, experimentalists. Yeah.
I think the photo is the experiment. Yeah.
The photon is the experiment my colleagues did, yeah, yeah. The Majorana, the Microsoft experiment, so they can't manipulate anions in terms of moving them around yet. But what they can do is measure Majoranas. So that the latest experiment they've done is by measurement. And the thing is that they can take advantage of the one-way quantum computation, and you can prepare complex states, and then by measurement, you can manipulate.
Lab in China in Taipei?
That's right. Yes, that's right. No, we did that experiment. So the Microsoft people, they've done something quite amazing in the latest work, that they perform measurements on these Majoranas. Now, they haven't proved there are Majoranas, but they've proved that they can do measurement on the system they have. And if they have Majoranas, they can manipulate information similar to one-way quantum computation, where you construct a large entangled states, and then by measurements, you manipulate your information. So yes, it is a very important step. I want to talk about that. Oh, the next thing we did is even more complex. We added yet another chain here, and we could do control NOT gates, or we could do all these different links and calculate the Jones polynomials of these links, or Kaufman brackets, if you like, and find the corresponding Jones polynomial. But constructing really the links out of word lines. Okay, maybe let me, so similar things we did with DS3 anions, but let me, and Jones polynomials, that's right, yeah. That's right. So it's been shown that Jones polynomials of certain types of anions are computational primitives. You can do universal quantum computation. Majoranas cannot be quite universal. You need to add some interactions between them, some known, but you can use magic states actually together with Majorana fermions, some specially entangled states, simple actually to construct, and you can do universal quantum computation. Actually, with this DS3 model, what we demonstrated that you can, first of all, we did a simple experiment which became a cover of PRL, because experimentalists use this very beautiful color, pastel colors. I highly recommend them in your papers. They can create a cover page of the journal. So even if it was classical light, but the DS3 anions, we do them, hopefully we'll show in our next paper to come out soon, is that you can construct magic states with them. So you can do universal quantum computation. And so we'll demonstrate in our next article that experimentally that you can construct universal quantum computation. And the good thing with the DS3, why we switched from Majoranas to that, is because this model is based on actually qubits, so not on fermions. So we don't need to do a Jordan-Wigner transformation. We can manipulate spins, much more complex manipulations, but it's doable. And the final thing is that we did very small prototype encodings, right? One is like that. The other is like a plaquette with 4 or 2 spins, actually. And what we noticed is that if I introduce errors in my system, like decoherence errors, here's a decoherence channel. I put an operator or a state O. I subject it to certain environmental errors, UE. It can be Pauli matrices or higher dimensional matrices, X, Y, and Z, with certain probability P for the error to happen. So introduce this type of errors on all my spins or qubits here. And I measured the final fidelity of what comes out. And what we measured is that the fidelity of the states, of the encoded logical states. So I apply these errors on the physical spins, and I measure the fidelity of the encoded anionic states. And what we found is that for small errors, the encoded one, which is the blue line, performs better than the non-encoded information. If I had the errors acting on the, if I encoded my information on the spins and acted with errors, then I'll get this straight line. The fidelity will go down. But if you encode the information on these systems, it stays up. This is not a topological protection. This is more of an encoding protection. You use more physical qubits to encode a small number of logical ones. And that created a protection, actually, that was unexpected. Also, this emerges only for small errors, but this is where, and it's a small improvement, but that's where the fight now is you want to improve, not to make 90% into 95. We already have 99% of fidelity. We want to push it to 99.9999. So such types of fidelity improvements by physical encoding are quite important. And with that, buy the book or download it from my webpage for free. Yeah. It's on purpose. I removed all mathematical language in it, which hopefully doesn't alienate the people here. It's just I have 0 mathematical language in it. There are formulas, but I don't use isomorphisms or category theory. I wanted something that an undergrad physics student can pick it up and read it through. And indeed, I made my master students proofread it, so it's doable. Yeah. When? 2012. A long time ago, yes. I think so. It's been translated in languages and stuff, and they keep bringing checks, and I cash it on my local pub, and yeah. I give it all to charity. Yeah.
Pints of beer, not the pub.
Yeah, it's for a charity, so for children. So no, I don't give beers to children. Yes. Yeah. So yeah. Outlook. Yes, I do believe quantum simulations are important. They do bridge a gap, conceptual, and also the guide experiments, what signatures to look at, and what we expect to find. And what is the quantum error correction? I don't believe much in realizing physical anions with Hamiltonians and so on. I believe using all these systems to protect information for quantum computation algorithmically. That's more faithful to what we have at the moment. Yeah. So I believe in quantum error correction. Yeah, and thank you for your attention. look, first of all, there are gray areas. When you say see actual, you mean without Jordan-Wegener transformation. I could do it the same things with quantum double models. Still, you'll ask me, but I don't have a Hamiltonian. I'll tell you topological systems have 0 Hamiltonian. You tell me, but the geometry is not a 2-dimensional lattice. I tell you, topological systems don't have a metric, so to have a geometry. So you can manipulate things as you like. I think quantum double models is probably a very good starting point. We can realize them in the laboratory either as a simulation of the states or build something that I find quite promising is this Rydberg atom spin liquids generations that we are also working on. We try to build non-abelian spin liquids, but the simulation is extremely hard. Already they did the experiment with toric code. They reproduced the toric code once. I think that's very promising. So again, this is, they use the PXP model in 2 dimensions, and they have these valence bond states, and then there is this product states, and Lukin and his collaborators showed that there is an in-between phase that is a spin liquid of Z2, DZ2. They did the theory, and they did also the experiment eventually, which was very nice. Though the signature, they could find the signatures of the toric code of strings and so on. That's the beautiful thing. You can actually measure invariance against strings and expectation values and so on. And there's a Hamiltonian. You find the phase there, yeah, protecting. Now, how to generalize it to non-abelian anions is not straightforward. You have to build Hamiltonians that have the symmetry of the group there. We believe we have signatures of DS3, but while the toric code uses qubit type of Hamiltonians for the DS3, we need to use qubits. And the Hilbert space explodes really fast. So we can do smaller system sizes. Signatures are not very clean, but they're there. So we're excited about that. For me, that's what excites me at the moment. I'm not sure I'm a good judge of the total literature, but I think that's a good bet. And it's interesting physics there. I mean, it's beautiful. Yeah, that's the anion. That's Cambridge University Press choosing a cover wisely. Yeah, no, that's the anion. If you like this, actually, a friend of mine made 2 illustrations that are inside the book. Some artist illustrations in there. Calculations turned into art. So yeah, you get some art if you buy the actual thing. Yeah. Yeah, yes, elusive, but yeah, you can own it. Thank you very much. Thank you, guys.